Okay, so hello everyone, and welcome to the Dandelion Physics series, and today's video will be about our second lesson upon topic 1.2. Okay, so in the previous classes, we learned about the idea of the random error, which means that in this class, we're going to be covering the concepts of the systematic error. Okay, so by definition, systematic error is a consistent, repeatable error associated with the faulty equipment or a flawed experiment design. And so, the random error that we talked about before is completely random, which means that we don't know whether our next measurement is going to be higher or lower. We have no idea. We are lost. But here, systematic error. So if we have a systematic error in our experiment, then hooray, like really hooray, then we know that it's going to be either higher or either lower. So it's only going to be one of them. So it's like always higher or it's always lower. So that will be kind of, how do I say it, like more like nice. Yeah. Okay, so systematic error is usually due to the following reasons. Sorry. So the first one is the faulty apparatus, your zero errors. So let's say that so I have a stick here and I'm trying to measure the length of this stick. So you have a ruler, and we know that our ruler doesn't really start from zero. So zero like might be here and blah 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 one and then two. So it doesn't start from like the point here. So, but that's where we want it to start, but it's not. So sometimes you always measure from here. So now you have a systematic error that the measurement that you are taking is always lower. Okay, and then the imperfect instrument. So the instruments that you are using in your experiments might be too old, or it's losing some parts, or it's simply really not accurate. So what it's like your instrument is just too bad. And then the next one, the incorrect methods, which means that the method that you are using when you're measuring the values are just incorrect, and there are a lot of mistakes included in your method. And then the last one, a really classic one, and that's the instruments not being calibrated. And what do I mean by calibrated? So that's the concept of the calibration of the instruments. So by definition, calibration is a comparison between known measurement and known measurement. That will be your standard with the measurement using your own instrument. And what do I mean by that? So here is an example. So I have two weights here, the first one and the second one. So the first one is 100 gram and the second one is 200. And here is something special about them. A weight, when I say it's 100 gram, it's exactly 100 gram. It's not higher, it's not lower. It's exactly 100 gram. So this is really, really accurate. It's exactly that value. So it can't be wrong. It's just that value. So when I put this weight on my weighing scale, and I see what's my reading here. So now, surprise, surprise, it might not be exactly 100.00 gram here. So your reading might be 100.01 or 100.02. And then you use another one. Okay, wait, let me remove this. You use your 200 gram and you put it on here. And here it might say, oh, this is 200.02 or 200.01 gram. And here you notice something that, oh, something is going wrong. So here you have to calibrate your instruments by every measurement that you're going to make later, so you know that every measurement is by how much higher or how much lower. So here you can actually fix your your systematic error. Yeah. Okay, so here, and then I have to tell you that the calibration of instruments is being applied on every single instrument that you are going to use. So it's not because, oh, my instrument is too bad. It's not due to this reason two here. It's not because your instrument is too bad. No matter how good or accurate or expensive your instrument is, you always have to calibrate it. Okay, then. So systematic error, as I mentioned before, is predictable. So it's either higher or it's either lower. So in your experiments, it's gonna be always higher or always lower. So really neat and nice. And that being said, the direction of the error is only one-sided. The direction of the error one-sided. So the direction here is only going to be like left or right or up or down or higher or lower. Yeah, so random error that we talked about before, the direction of the random error is two-sided. It means that it can be higher or it can be lower. You don't know, you have no idea. It's completely random, and that's why it's called a random error. It's not predictable. But however, systematic error, on the other hand, is predictable and consistent. So here, it's in one direction only. So it's either always lower or it's always higher. Yeah. And if I'm going to represent this on a graph, so here. So the first graph is in terms of our random error, and the second one is in terms of our systematic error. So here, let's say that, for example, that you are doing an experiment right now, that you are trying to investigate the relationship between the number of hours that you sleep and the amount of homework that you can complete. So theoretically, or in this case, I assume that the theoretical relationship between these two variables here, they are directly proportional. So it will be a linear line that passes through the origin. That's what I mean by directly proportional. And that's a key point here. So when I say directly proportional, so it's going to be a linear line, of course, but here it has to pass through this origin. It has to pass through here. So you can say, oh, this is directly proportional. So when I do this or this or this, they are proportional, but they are not directly proportional. Okay, so back to what we are saying here. So here, this is the theoretical trend, the theoretical relationship here. So, but however, now you have a random error, which means that the value that you measure can't just be like exactly on the line. That would be too perfect. So if you have a random error, then on a graph, you'll be like this. Boom, 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 like higher, lower, higher, lower, higher, lower. And when you draw the line of best fit, it's going to be this. But however, the value that you are getting is higher, lower, higher, lower, higher, lower. And then, in terms of the systematic error, so this is our theoretical line that passes through the origin. Nice. And then here, so we say that the systematic error is going to cause your measurements always higher or always lower. So if it's always higher, so it will be something like this. So the value that you are getting is this. And when you draw the line of best fit for this, like for this series of data, it's going to be like this. So you know that, oh, relative to the theoretical value here, the measurements that I'm getting has a has a systematic error. So it's going to be, oh, it's always higher. Or it can also be, oh, it's always lower. So the line of best fit here, so you know that, oh, it's always lower. So first, you have to know, like, where is your theoretical line. So I know where this is, so then I can predict. I know that, oh, am I being higher or lower? Okay, then. So in previous class, we talked about that random error can only affect your precision. So intuitively, we can think of that systematic error can only affect the accuracy. Okay, so this only affects this. So here, our old diagram here. So if it's only affects accuracy, it means that, so here, so if it's always lower, then it will be like this. Or if it's always higher, then it will be like this. Like whether you are being precise or not, it's just going to be always higher or always lower, which means that you are always higher or lower relative to your correct value. And that's why it affects your accuracy, because accuracy means that how close is the value that you are getting comparing to the correct value. So how close is your value and the correct value? So if the systematic error is going to cause me to move away higher or lower from this value, then it's going to affect my accuracy, right? Okay, my accuracy here. Yeah, and that's the idea that systematic error only affects accuracy. And then, how do we reduce it? How do we reduce systematic error? So, like in previous class, we talked about that if you want to reduce the random error, which you can only reduce it, and then, well, it's like you have to do a lot of trials, and then when you average them, so that will be really close to the correct value. So here, if you want to reduce the systematic error, the two popular approaches are here. So the first one is that you calibrate the instrument as we talked about before and check for your random error. Check for your zero error. And then second one, improve your method, which means that you're going to improve the design of your experiments. So here is an example. And fun fact, did you know that if a object is in a really high temperature, then its mass will be less than when it's in a lower temperature, which means that when I'm trying to measure the mass of this heating pot here, if I'm measuring in 100 degrees Celsius or when it's in 20, so that'll be like the room temperature. So here might be 100 kg, so here might be 110 kg. So here, if you try to measure the mass of this pot, then you should wait for it to cool down first. Then you are going to get a appropriate or a more accurate value that you are trying to find. But if you always just measure it right after you heat it up, then the value that you will be getting for your mass will be always lower, and that creates a systematic error. You have to improve on your method and like that in order to reduce your systematic error. Okay, so that's all from us today, and if you have any questions, please comment down below, and if you would like to stay tuned for further videos, please click subscribe, and I will see you next time.